Okay, can we just skip the rant this time? I have been talking about multiplication for way too damn long here. Let's just breeze right through this. Yeah, theme song. Great. So, last episode we saw two strategies for doing mental math. Tirthaji's method and Trachtenberg's method. Let's move on to our third strategy. You might have heard rumors that Japanese school kids are able to add insanely long lists of numbers in their heads, along with multiplying some pretty big numbers too, making the adults among us feel really incompetent by comparison. The deal is, the Chinese invented a type of abacus called the swanpan, which made its way to Japan sometime around the 1300s. The Japanese were like, what's with all the extra beads, and simplified it into what they called the soroban. Soroban is just Japanese for abacus. Wait, Japanese abacus? Hey, Feynman had a story about that. I know Feynman had a story about that. Feynman had a story about everything. Shut up about Feynman already. Now about the soroban. Each column represents a decimal place, and each particular arrangement of the beads corresponds to a particular number. The bead up top represents 5, and each bead on the bottom represents 1. When the beads are moved close to this middle bar here, called the reckoning bar, you count them. When they're moved far away, you don't count them. So you'd count up from 0 like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. If you want to go up to bigger numbers, you start to use the next decimal place. So 10 is 1, 0, 11 is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, you get the idea. Okay, so how does addition work on this thing? Let's do 25 plus 13. You start by writing down 25 on the soroban as 2, 5, and then to add 13, you just add 1 bead to your tens place and add 3 beads to your ones place. Then you can read off the answer as 3, 8, or 38. It does have some nuances involving borrowing and carrying. For example, if you have to do 18 plus 27, you start by writing the 18 down, add the 2 in the tens place, then suddenly you're left with a problem. You have to add 7 to the ones place, but there aren't enough beads for that. What you're supposed to do is tell yourself that adding 7 is the same thing as adding 10 and subtracting 3, but that's too much work for me. I just do 7 plus 8 in my head, get 15, add the 1 to the tens place, and turn the ones place into a 5. Either way, you get your answer of 45. It's particularly useful for big numbers. If you had to do 1, 2, 3, 4 plus 5, 6, 7, 8, you just write down 1, 2, 3, 4 and add 5, 6, 7, 8, one digit at a time, so that's not too bad. Well, once you get over the annoyance of carrying and moving that damn 5 bead back and forth anyway. So, how does the soroban do multiplication? It doesn't! You don't do multiplication on the soroban, you do it in your head. What? The way you do multiplication on the soroban is that you don't do multiplication on the soroban? What the hell? How does that help? For small products, it doesn't. To do 8 times 7, you still need to rely on your own memory to tell you that the answer is 56. The way the soroban helps to do bigger products is that you multiply each digit in your head one at a time, and then you use the soroban to keep track of those products and add them all together as you go. So if you had to do 8 times 36, here's how it works. You start by writing down the 36. Then you write down the 8, just so that you can remember what number you're trying to multiply by. You write it with 2 empty digits between the 8 and the 36. The reason being that when we multiply stuff, we might end up having to do some carrying, and carrying will move stuff over 1 digit to the left, and we don't want to accidentally write over our 8. So you'd start by doing 8 times 6 in your head and getting 48. You write the tens place one spot to the right of the last digit of 36, and the ones place the next digit over. Okay, so we've done 8 times 6, so now we can get rid of the 6 part. It's already been multiplied out, so we can just clear it right off the board. Then we move to our next digit, 8 times 3. We get 24, so again, we put the tens place one spot to the right, and we put the ones place the next spot to the right. We clear off the 3, and we get our answer, 288. Nice. Let's do an absurdly big product, just to show we can. The website offers the example 1329 by 567, and I'll be honest, I keep screwing this one up, because I keep losing track of what decimal place I'm looking at. The little dots are supposed to help with that, like one of the dots is the ones place, the next dot 3 spaces over is the thousands, and so on, but it's still kind of tricky. Okay, here goes. So we write down 1329 like that, skip 2 spaces, write 567 like that. Okay, now, the first thing we're going to try to do is kill off this 9 here, so we're going to multiply every part of 567 by 9, starting with the bigger digits. So 9 times 5 is 45, 9 times 6 is 50, 4, carrying sucks. And 9 times 7 is 60. Oh, come on, 3. Clear 9. Okay, so far what we've got is 567 times 9 is 5103. Is that right? All right, good deal. Moving on. Now we're going to try to kill off this 2 next. So 2 times 5 is 10. 2 times 6 is 12. 2 times 7 is 14. Clear 2. So now we've done 567 times 29 and got 16443. Still right? Awesome. Next digit. Gotta kill 3, so 3 times 5 is 1, 5. 3 times 6 is 1, 8. Oh my god, carrying, why? 8 and 6 is 14. Okay, like that. And 3 times 7 is 2, 1, clear 3. Okay, so far we've done 5, 6, 7 times 3, 2, 9, and we have an answer of 186,543. Is that right? Good deal. Alright, let's finish this up so I can go home and make waffles. 1 times 5 is 5. Uh-oh, careful, just 5, not 5, 0, so we gotta skip a space and drop it over here. 1 times 6 is just 6, so it goes here. Oh, more carrying. And 1 times 7 is just 7, so it goes here. And oh, look at that, one last little bit of carrying as a final goodbye. Thanks, problem. I love you too. Okay, so our answer is 753,543, or 753,543. Is that right? Hell yeah! Take that, Japanese elementary schoolers. You can't make this guy feel insecure. I can use the Soderbond too, see? The only advantage you have is that you can do it faster, and with fewer mistakes, and entirely in your heads. But I don't feel insecure. Nope. Wait, what was that about being able to do it all in their heads? It turns out that over the course of 2 or 3 years, the students start to learn how to move the beads without looking at the board, kind of like learning how to play the guitar without looking at the strings. Then they don't even need a real Soderbond. They just drum their fingers on the table and pretend they're moving beads around, like they're playing air guitar. And then they don't even need to move their fingers. They just picture moving the beads around in their heads. That's called Anzan, or blind calculation. It's a combination of tactile and visual memory internalized through lots of practice and repetition. So apparently, once you have enough practice with the Soderbond, you don't need to carry one around anymore. The downside is that you're still stuck having to do partial products in your head, and you might need to practice this for years before you get good at it. Man, this video feels like it's taking years. Why do I have to talk so damn much? Last strategy. Want to learn magic? Some people can multiply random 2 or 3-digit numbers in their heads, along with finding the squares of 2, 3, 4, or in some cases 5-digit numbers. These spooky math wizards are sometimes called mathemagicians because they perform these stunts as a part of a magic show. We're indebted to one mathemagician in particular named Art Benjamin who spilled the beans on how it all works. To multiply any pair of 2-digit numbers, there are 2 really helpful shortcuts. You can either use neighbors or factoring. Neighbors means you just look for an easier product that happens to be nearby. For example, 34 times 99 is just 34 times 100 minus 1. So that's 3400 minus 34. Then you can just use complements or whatever to get 3366. Factoring just means that we look for how we can rearrange the factors of products to make them easier to do. For example, 24 times 18 is 24 times 9 times 2. So that's 180, 36 is 216. So 216 times 2 is 432. It's usually easier to group the bigger numbers together, so doing 24 times 9 then multiplying by 2 is a bit easier than doing 24 times 2 then multiplying by 9. Those 2 rules cover most cases for multiplying 2-digit numbers. If you randomly pick a 2-digit number, chances are that it's divisible by 2, 3, 5, or 7, so the factoring trick will work most of the time. Otherwise, you can use the neighbors trick to take care of the numbers that are only 1 off from multiples of 10. That only leaves a small handful of cases, which can kinda still be solved using the neighbors trick, it just takes more work. Okay, so that's how mathemagicians multiply pairs of random 2-digit numbers. Now, how do they find the squares of 3, 4, and 5-digit numbers? If you had to do 49 squared in your head, that's kind of tricky. It would be easier if we could do multiples of 50 instead. So we have to go up by 1 to go from 49 to 50. If we went down from 49 by the same amount, we'd get 48. So if we multiplied 48 by 50, we'd get an answer very close to 49 times 49. 48 times 50 can either be done as 48 times 5 times 10, or as 48 times 100 over 2. Either way gets us an answer of 2400. So 49 squared is something very close to 2400. How close? To get an exact answer, you just add the square of however much we went up and down from our original number. In this case, we went up and down by 1, so we tack on an extra 1 squared to the end of our answer. So our answer is 2401. You could do 32 squared in your head the same way. You say to yourself that multiples of 30 are easier, so you go 2 down from 32 to get 30, you go 2 up from 32 to get 34, and you multiply 30 and 34 together. 30 times 34 is just 3 times 34 with an extra 0 at the end. So that's 90 and 12 is 102, so 1020 or 1020. And then to finish the answer, you just add 2 squared. So it's 1020 and 4 is 1024. Now, this trick can be used for larger products too. It turns out that Art Benjamin has been squaring numbers this way for so long that he's managed to memorize all the squares of 2-digit numbers. Damn you people and your ability to memorize stuff. So if he has to do 314 in his head, he goes up by 14 and down by 14, multiplies 300 by 328 to get 984 with 2 zeros at the end, and then he just knows that 14 squared is 196, so he can add that to get 98596. So for most of us, this strategy is useful because since we know the squares of one-digit numbers, we can use this strategy to find the squares of two-digit numbers. But if you happen to know the squares of two-digit numbers, you can also use this strategy to find the squares of three-digit numbers. Another nice thing about this method is that you start by multiplying the larger numbers, the numbers on the left, first. That's useful for two reasons. First, it reduces your chances of screwing up the numbers on the left, which are the biggest and most important digits. And second, it lets you calculate the smaller numbers while you're saying the bigger ones out loud. That makes it look like you knew the whole answer all at once, even though you're only figuring out the digits one or two at a time. You sneaky devil you. Now, how do you square a 4 or 5-digit number? You do it the exact same way, but this time you throw in a mnemonic device to help you keep track of the numbers as you go. It's called the major mnemonic system. The basic idea is this. Numbers are hard to remember, but sounds are easy to remember. So you associate each number 0 through 9 with a particular letter of the alphabet. Then you turn those letters into sounds. So if you had to remember the number 170, you can represent that with the letters TKS or DKZ or something. And to make that into a word, you just throw some vowels into it. In his performance, Art Benjamin did 5217 squared. Oh boy. Alright, so we're going to go up by 217 and down by 217. That gives us 5434 times 5. We'll worry about the zeros later. So that's 25, 27, 27,150, 27,170. When we bring back those extra two zeros, it would be 27,170,000. Now my memory is at its limit here, but we still have to add 217 squared to get our final answer. How are we going to do that? Well, if we know there won't be a lot of carrying, we can just say the 27 million part out loud to get it out of our memory and into the audience's. We just forget all about it after we say it. Then we're just stuck with having to add 170,000 to 217 squared. Now we have to calculate 217 squared, but we can't do that when we still have to remember the number 170,000. So here's where we'd use the major mnemonic system to convert the numbers 170 into the letters DKS and turn it into the word ducks. As long as we can remember ducks, it's safe to calculate 217 squared without forgetting anything. To do 217 squared, it's the same method as before. Go up and down by 17. 234 times 2, worry about the zeros later, is 468. So that's 46800 plus 17 squared. 17 squared is 170, 70, 49. It's 240, 49. That's 289. But of course, Art Benjamin just memorized that one. So 46800 plus 289 is 47089. Now, we got to add the thousands place of this number to the thousands place that we stored as the word ducks. But if we try to do that right away, we're going to forget what these last three digits here are. So we store those three numbers, 089, as the letters SVP, or save up. Okay, so we have to add 47 to ducks and tack on save up at the end. Now we can convert ducks back into a number. 47 plus ducks is 47 plus 170, so that's 217. So now we can say out loud 217,000. Finally, we bring save up back as a number, 089, so we can say the last part of our answer, 89. So the whole answer is 27,217,089. Although we never actually knew all of that at once. We just sort of said the millions place first and then forgot about it, said the thousands place and then forgot about that, and then said our last few digits. Okay, while that's exhausting, the cool thing is that you really only need to do the same two tricks over and over. Trick number 1 is that you go up by a bit, down by a bit, multiply, and then add the little bit squared. And trick number 2 is that in order to remember stuff, you convert the numbers into letters. Art Benjamin uses these same two rules when he's doing the squares of 5-digit numbers. He just has to store a whole bunch more numbers in his head as words and say them a whole bunch of times over and over to keep from forgetting them. So that is how people can square 2, 3, 4, and 5-digit numbers in their heads. Now you can impress all your friends with that. Okay, so in summary, we've looked at 4 different strategies for alternative multiplication. Tirthaji shortcuts really come in handy for multiplying numbers that are close to multiples of 10, which is helpful, but also kind of taxing to remember 4 different numbers in your head at the same time. Trachtenberg's method lets you generate all the digits of a product without ever having to multiply or divide by anything bigger than 2, but it forces you to know the 9s and 10s complements and write the digits down as you calculate them. The Soderbaum technique lets you combine tactile and visual memory to keep track of lots of different partial products in your head to make it easier to add them all together, but it takes a really long time to practice. And the Mathemagic strategy is useful for multiplying most 2-digit numbers, but requires special memory tricks for bigger numbers. if for some sick, horrible reason you actually want to learn more than that about multiplication, you're on your own because I am so finished talking about it. It's time to finally move on to something exciting like quantum mechanics or relativity or division? Seriously? I have to spend an entire episode on division? Oh, this is bullshit!